So what happens in an equilibrium system when you cause what's called a disturbance, okay? First of all, what the heck is a disturbance? A disturbance means you've changed something to that equilibrium system. And here are 4 different ways you can cause a disturbance. You can take something out. You can take some of the reactant out, take some of the product out. Imagine you're a company and your company's job is to make NH3. NH3 is ammonia. It's used in cleaning, it's used in fertilizers. It is a huge, huge business. The problem is it creates an equilibrium system. Okay, you don't want this part, you want this part. You want to try to force this reaction to go as far to the right as possible so you can make more NH3, therefore you sell more, you make more money. Okay, and so a lot of times we can cause these, again, disturbances to happen that we're trying to cause the reaction to shift in one direction or the other. So again, some of the ways you can do that: number 1, you can add or remove a reactant or a product. Number 2, you can change the volume. Number 3, you can change the temperature. And number 4, you can add a catalyst. So let's talk about that first one. What happens if you add or remove one of the reactants or products? Okay, when we add a substance, so if you add something, so let's say we add some more nitrogen or some more hydrogen to this reaction. Okay, so we put some more nitrogen or hydrogen in there. The reaction will shift to reestablish equilibrium by consuming that added substance. Okay, and so what it's going to do is it's going to shift to the opposite side of the equation. So here, if I add some H2, if I add some H2, that's going to cause a shift to the right. Okay, if I add some NH3, that's going to cause a shift to the left. Anytime you add something, it shifts to the opposite side to consume that with the stuff that you've added. Okay, now what if you take something away? If I remove some NH3 from the container, the reaction is going to shift. That's what it says on here. Conversely, removing a substance will cause the reaction to move in the direction that forms more of that substance. Okay, so with N2 and 3H2 NH3, if more 2 is added, it's going to shift to the right. So more O2 is added, it's going to shift to the right. Okay, if some N2 were removed, again, N2 is a reactant, so if you remove some of that, it's going to shift to the left. Okay, now none of these things cause the equilibrium constant to change, so the equilibrium constant will still stay the same. Okay, so it's going to shift to the right, it's going to shift to the left, but the value of the equilibrium constant doesn't change. So here you can kind of see what it does. If we add some hydrogen, what happens to the amount? Here's the pressure, right? The amount of hydrogen goes up, but then after it goes up, it's going to shift to the right. So then the amount of hydrogen is going to go back down a little bit, along with nitrogen. Okay, both of the reactants are going to go down, and then the products, NH3, is going to go back up, and now we've reestablished equilibrium. Okay, what if you change the volume of a equilibrium mixture? Let's say you make the container smaller. Well, if you do that, the reaction is going to shift to the side with the fewest number of gas molecules. Okay, so reducing the volume causes the pressure to increase. Okay, and the system shifts in the direction that reduces the number of moles of gas. Okay, and obviously the opposite is also true. If you make it bigger, if the volume increases, that decreases the pressure, and that's going to shift to the side that produces more gas molecules. Okay, for example, here we've got N2O4. We've got 1 gas on the left, and we've got 2 NO2, so we have 2 gases on the right. If the volume is decreased, the pressure goes up. And if that happens, then the reaction is going to shift to the left-hand side to form more N2O4 because, again, it reduces the total number of moles of gas. There's 2 on the right and only 1 on the left. Okay, for N2 and H2, that reaction, again, you've got 1 nitrogen and 3 hydrogen. So you've got 4 gases, and here you only have 2 gases. So a volume decrease will cause the reaction to shift to the right, since there's only 2 moles of NH3 for every 4 moles of the reactants. Now, again, let's think about this in terms of I'm trying to produce some ammonia. I want to produce as much NH3 as I can. Do I want to do this under a high pressure situation or a low pressure situation? Okay, and if you think about what happens when you decrease that volume and the pressure goes up, it's going to shift to the right and make more ammonia. So you would want that. You want that volume to decrease and you want that pressure to be nice and high to force that reaction to shift to that right-hand side. So again, when you add a reactant or a product or take some away, that does cause a shift to occur, but it does not cause the equilibrium constant to change. Okay, when you change the volume and the pressure goes up or the pressure goes down, again, a lot of times a shift will occur, but again, it does not affect the value of the equilibrium constant. Okay, now let's talk about a couple other things. What if you add a gas that's not involved in the reaction? Let's say you add some NO2 to that reaction with N2H2 and NH3. Okay? If you add a reactant that is not involved, like here, if you add some argon, of course it makes the pressure go up. Okay? But remember what we learned about gases. It does not affect the partial pressure of the other gases and will not cause a shift in the equilibrium. Okay? So, you add a gas that's not involved, it doesn't cause a shift to occur. If you add a gas that is involved, we already talked about that, right? If you add some more N2 or some more H2 or some more NH3, then absolutely yes. Okay, it does cause a shift to occur. Okay. So a couple more things. So when a temperature change happens, so let's say we raise the temperature of an equilibrium system. Okay, that's the time that it does cause a change in the value of KEQ. Okay, the equilibrium, this is the only time that the equilibrium constant will change is when you change the temperature. Okay, when the temperature is increased, so if we make it hotter, it's like we've added a reactant or a product to the system at equilibrium. Okay, the equilibrium shifts in the direction that consumes the excess reactant or product, which is the heat. So, this is much more involved than just general chemistry, but if I tell you it is an endothermic reaction, okay, that means that the reaction is taking heat from the surroundings. Usually when you feel that, it feels cold. Okay, so an endothermic reaction is taking heat from the water or from the air, and so it feels cold when you touch it. Okay, when it is endothermic, notice where you put heat. You put heat on the reactant side. Okay, because it's taking that heat. It's using that heat to make that reaction happen. Okay, in an exothermic reaction, it's releasing heat. And that's when you feel it. You go, oh man, that reaction, that's hot. Okay, it feels hot because it's releasing energy. It's producing energy. And notice that energy, the heat, is on the product side. So all you need to remember from this is endothermic is heat is on the reactant side. Exothermic, heat is on the product side. And then if I raise the temperature, let's look at exothermic. Okay, if I raise the temperature, that means I'm increasing the heat. What does the reaction do? It shifts to the left. Just like if I add more product. If I add more product, what does it do? It shifts to the left. If I decrease the temperature, if I lower the heat, then what does the reaction do? It's going to shift to the right to make more. Okay, just like it's a product or a reactant. You just need to remember, if it's exothermic, the heat goes on the product side because it's releasing heat. The heat, I think of it as exo, like exiting. The heat is exiting the reaction, so it's on the product side. And then with endothermic, I kind of think of into, like it's going into the reaction. You need it, so heat goes on the reactant side. Okay, and then the last thing, just a quick mention of what are called catalysts. Catalysts are something that make reactions go faster. Okay, but the important part, catalysts do not change the composition of the equilibrium mixture, so there is no shift that happens. Okay, so if you add a catalyst, you get to equilibrium faster, but it does not cause the reaction to shift to one side or the other. Okay, let's look at a couple of examples here. So, we've got, again, so in what direction will the equilibrium shift when each of the following changes are made? If I add some N2O4, that means I'm adding some reactant. And the reaction is going to shift to use that up, to consume it. And so that will cause a shift to the right. Okay, if I remove some NO2, NO2 is a product. If I remove some, the reaction is going to shift to make more. That's also going to cause a shift to the right. Okay, what if I increase the total pressure by adding some nitrogen? Again, N2O4 is in this reaction, and so is NO2, but N2 by itself is not involved in the reaction. So what happens? There is no shift occurs if you add some nitrogen. Okay, letter D. If I increase the volume, that means the reaction vessel gets bigger, the pressure is going to go down, and when the pressure goes down, it can spread out more, so it's going to make more gas particles, so that's going to cause a shift to the right. Okay, the only time that doesn't happen is, let's say we have two, and again, I'm making up fake elements here, plus B gas makes 3 C gases. In that case, notice we have 3 gases on the left and 3 gases on the right. When that happens, when you increase the volume or decrease the volume, which way does it shift? Well, if the number of gas particles are on the same on both sides, then there isn't going to be a shift, okay? There can only be a shift if there's a different number of gas particles on each side. Okay, and then letter E, assume the reaction is endothermic. Okay, if it's endothermic, that means we put heat on the reactant side. And if we lower the temperature, it's the same as if we took some N2O4 away. We're taking some heat away, and so what's the reaction going to do? It's going to shift to the left. Okay, and again, that's the time where, if in this case the products are going down, the reactants are going up, this is the only time that the value of KEQ changes. Okay? So, LeChatelier's principle is just a great way about when a disturbance happens to an equilibrium system, how does the reaction shift to counteract that to reestablish equilibrium?